Hello everyone and welcome back. This is the part 2 of the video series where I explain my first research project that I did as a PhD student to fulfill my thesis work at Michigan Technological University. Now in the last video I gave an introduction about the radial basis function method because my research project is about using the radial basis function method to solve partial differential equations where they have applications where the applications are from geoscience field. Now in this video I'm going to give the application problem. I'm going to explain the application problem that we solved, and then also I will present our numerical results in this video. Alright, so here's the governing partial differential equation. Now this partial differential equation is called the Drawdown equation. Now this equation models the water level decline when you pump water from a well. Now that's why this equation is called the drawdown equation. We want to calculate the drawdown in the underground, drawdown of the water level when you pump water from a well. Now let's learn about this equation. So simple lowercase s represent the drawdown, and simple t represent the time. Capital Q is the abstraction rate. That means when you pump water from the well, the abstraction rate of the water. And then capital T is the transmissivity, capital S is the storage coefficient. I will explain those two terms in the next slide, okay? But for now, in this slide, the most important thing in this equation is that this equation contains a delta function, a mathematical singularity. Now that's how this equation represents the well. So delta function represents the well. Okay, and it's a logarithmic singularity. Now we want to solve this partial differential equation initially on a rectangular aquifer. So that means the domain looks like a rectangle, and with the partial differential equation, of course, you definitely need boundary conditions. So you have imperable boundary conditions. That means on the top and the bottom there are imperable boundary conditions, which we call the Newman boundary conditions in math. And then on the left side and the right hand side of the rectangular domain, we have what's called the Dirichlet boundary conditions. So this is the partial differential equation that we solved first. Now this equation is in its simplest form. There's another form of this partial differential equation, but we will look at that later in this presentation. Alright, so we already know what's drawdown. Now storage coefficient is the volume of water released from the storage or taken into the storage per unit of aquifer storage area per unit change in the head. So that's storage coefficient. Now transmissivity, that's very important in this equation. Now transmissivity, you can think it like this. Now when you have water in the underground, it goes through many different mediums. There's rocks in the underground, there's sand in the underground. So in different medium, the speed that water travels differs because of the permeability. So this transmissivity takes that into account. So transmissivity is very important in this partial differential equation. So that's what was represented by capital T in the partial differential equation. Now abstraction rate, the rate at which the water is pumped, that's what represented by capital Q in the partial differential equation. So that's a brief introduction about the partial differential equation. Now we talked about the domain that we solved the partial differential equation. So a rectangular domain, and as I said, in the top and the bottom part you have Newman boundary conditions, and on the left and the right we have Dirichlet boundary conditions, and we assume the well is in the middle of the domain. It doesn't need to be in the middle of the domain, but let's assume that it's in the middle of the domain, and coordinates of the well are eta and neta. Okay, so that's the introduction about this partial differential equation. Now remember I said that this PDE is in its simplest form because you know what, we can actually solve this partial differential equation without a help of a numerical method. That means for this PDE we have an analytic solution. So this is how the analytic solution looks like after one day, the drawdown after one day. Now this picture is in upside down. Okay, we should flip this picture, but it's upside down, it's flipped because to visualize it better. Now if we have a analytic solution for this PD, why would we want to solve this PD using a numerical method like RBF method? The reason is that first we want to solve this version of the PD and we want to do an error analysis. We want to see how good or bad our method is. So that's why we started with the simplest form. So we call this a benchmark problem. Alright, now if you want to use a regular numerical method which requires a mesh, you could run into several problems if you decide to use a mesh. The reason is that, as you know, in the middle of the domain we have a delta function, a mathematical singularity, because that's how the well is represented mathematically. Now if you're using a mesh, you have to refine the mesh along this cross-sectional area that's crossing the well, and refining means you need to have tiny, here our mesh is constructed using the polygon rectangle, so you must have extremely tiny rectangles on this cross section area and larger rectangles outside this area. Now this can be expensive, and not only that, this can lead to small time steps. I'm sorry, it's a tongue twister. Small time steps. Okay, now this is called the CFL condition in numerical analysis. Now small time steps means when you solve a partial differential equation numerically, a time dependent one, if you want to find the solution after one day, you have to march to the day one. Like first you find the quarter day solution, then half day solution. So likewise you have to slowly march towards the final destination. Now what happens with the mesh refinement is that this march is going to be extremely small, like 0.1 days, 0.2 days, 0.3 days. Now this can be computationally expensive. Okay, and that's the problem with using a mesh in this scenario. Right, and the other thing is there's another method that you can use to solve this PDE, which is called the analytic element method. Now you can use the analytic element method to solve this partial differential equation, and it's a very nice method, but the problem is that you cannot solve this same PDE in this same PDE's next form. You cannot solve it using the analytic element method. We will learn what's the next form of this PDE in several minutes. Okay, all right, so that's what people do. That's how people solve this partial differential equation nowadays. There's software generated by MODFLOW which use the finite difference method, which uses a grid just like this, a mesh just like this, and the problems, now I have explained the problems that you could run into if you use MODFLOW or if you use a mesh based method to solve this PDE. Now we don't need a mesh to solve this problem because we use the radial basis function method and it only needs a node distribution. However, working with the delta function is complicated. This mathematical singularity can make your life hard. So we need to come up with a trick to handle the delta function in the partial differential equation. Now this is what we propose. Remember, when we use the radial basis function method, what we do is we assume the solution to be a linear combination of radial basis functions. So that's what we have here. But what we propose here is we are going to add an extra term to this assumption, which is a logarithmic term. Okay, now let me do this. Now I'm gonna say this summation, it can be represented by the variable v. So we assume our solution to be a linear combination of basis functions v plus another logarithmic term. Now in this logarithmic term, x sub w is the well location, q is the abstraction rate, and capital T is the transmissivity. Now the good thing is we know the well location, we know the abstraction rate and the transmissivity before we solve the problem. So keep that in mind. Now what we're going to do is we're going to replace this right hand side, we're going to substitute this right hand side into the PDE. Remember, the dependent variable of the PDE is simple s. Now it's gonna change to simple v. The reason is that the Laplacian of this logarithmic term is the delta function. What's going to happen is that when you use this special extra term, the delta function in the PDE is going to cancel out. And instead of having the PDE with the variable s, now you're going to have the PDE with the variable v. So through a substitution, we made a change of variables in the partial differential equation. Now, the nice thing here is that when you do this, you're gonna get rid of the delta function in the PDE, and it is represented by this logarithmic term in the solution. Now, working with the logarithmic term is super easy, easier than the delta function. And we can do this because, as I said before, we know the well location, we know the abstraction rate, we know the transmissivity before we solve the problem. That's the data that's given by geologists to the mathematicians. Okay, so we take the well contribution and we put that in the solution rather than putting it in the PDE. Okay, so now when you do that, all of a sudden you get a PDE which does not contain a delta function. Now, however, it introduces a tiny problem. The problem is that now your solution contains this extra logarithmic term. It's going to change the boundary conditions. Remember, we had nice simple boundary conditions. Now, all of a sudden your boundary conditions looks complicated. That's not a big issue, but we wanted to keep things simple. So what we proposed is that, okay, we want to solve this problem over this whole rectangular region. We're going to divide this region into two parts where the well is in the middle, and we take the first region to be a certain neighborhood of the well covered within a certain radius, a circle area, and we consider the other region to be what's outside the circle, this yellow color region. So blue color region and yellow color region. Now what we did is, in this blue color region, we performed that substitution, made that change of variables, and we have the PDE without the delta function. But in the yellow color region, we didn't do that substitution. We solved the same PDE as it is with the delta function. But the effect of the delta function is going to be, it's not going to affect because we are far away from the well. Now you might think, hold on for a second. Now instead of solving a one PDE, you're solving two PDEs in two domains. Yes, it sounds like that, but it is not complicated as you think. Okay, now it's the good thing about the RBF method is that you only need to change few rows in the differentiation matrix, and you're only solving the system once. So it's equivalent to solving a PDE, it's equivalent to solving a one PDE. This does not increase the computational cost significantly. Okay, still solving the problem is very computationally efficient. Now, as I said before, this PDE in the simplest form has an analytic solution. So what we did is we did an error analysis. Remember, we use RBF-FD method with polyharmonic splines, so we expect algebraic convergence, so we get high order accuracy. So if we desire, we can get third order accuracy, fourth order accuracy, fifth order accuracy. So we just need to change the RBF function, some changes in radial basis function, which I didn't discuss in my previous video. I didn't go into that depth. But if we desire, we can get fourth order accuracy, fifth order accuracy, sixth order accuracy without a problem. And we got these convergence plots, and we from these numerical results we can prove that our method works. So we successfully solved the first benchmark problem in its simplest form using the radial basis function method. So now it's time to move on to solve the difficult, complicated form of this partial differential equation. Okay, so now what's this complicated version of the same PD? Now here's the new partial differential equation. Okay, same partial differential equation, but there's a slight change. Now in the previous PDE, we had t times Laplacian s, but instead now we have divergence of t times gradient of s. What's the difference? I think I didn't mention in the previous case, but in the previous PDE, we assumed transmissivity to be a constant. Okay, that means the speed that water travels through different media is same. Now that's not a realistic assumption. That's not practical in real life applications. So that's why I said this is the important PD. This is the real version of the PD. Now capital T, or the transmissivity, is no longer a constant. Okay. Right, now we can use a little bit of vector calculus and rewrite this term, and then our left hand side will look like this. Now this is the heterogeneous case. Previous case is called the homogeneous case, by the way. Now this operator right here can be also little bit challenging. So we look at what MODFLOW does when they handle this operator. Now what they do is that they assume T to be piecewise constant function. Okay, so remember they have mesh, and when you use MODFLOW you have a mesh. So in each rectangular region, each small rectangular region, you can assume T to be a piecewise constant. Now all of a sudden this means again T is going to be a constant. So gradient of T is going to be 0. Again you end up with the same old partial differential equation. However, we believe that this is not an accurate representation of this realistic case. So we decided to take an alternate approach rather than assuming T as a constant like MODFLOW does. Okay, now you might ask why? What's the problem with this operator? Why do you think that it's challenging for us? Now here's the thing. When we solved the previous PDE, we had a nice trick. Remember? In the solution, we added an extra term, a constant times a logarithmic function, in order to cancel out the delta function, right? We did the change of variables. Now, if we do the same for this new version of this PDE, we will be not able to cancel out the delta term, because now not only we have this Laplacian function, so we have the Laplacian operator, but we have this extra gradient T and gradient S, so they will play a part and will not cancel out the delta function. In fact, it will leave us with another singular term. Okay, so that nice little trick does not work here. Okay, now we have to come up with a solution for this. Now remember, in the previous case, this special extra term that we added was a constant time a logarithmic function. Okay, so keep that in mind. Now what we did is that we looked at this left hand side, and we know it's going to have this gradient T term. So we assumed that this gradient T term contains smooth functions that contains Taylor expansions around the origin. So we made an assumption, and then instead of using a constant times a logarithmic function in our solution, okay, we said, okay, now our special term that we are going to add to the solution is going to be a polynomial times the logarithmic term. Now what's the effect here? Now still, when you add this extra term and when we substitute this into the PDE, you will end up with a residual term just like this. Okay, a singular residual term. But now what we are going to do is we are going to construct this polynomial P in a special way so that the singular parts of the residual term vanishes, and this R1, so you can see there are two parts of this residual term, what's going to left after substitution. We are going to construct the polynomial such that R2 becomes 0. So this extra logarithmic term that leave in the PDE is going to vanish, and R1 is going to be divisible by x square plus y square. So we are going to construct our polynomial so that we are going to end up with a residual term, but we are going to end up with a non-singular residual term in the PDE. Okay, so just to summarize, if we solve that all partial differential equation, simple one, when we do the substitution, it cancels out the delta function and will not leave a residual term. But now what we are going to do is we are going to add a polynomial in front of the logarithmic term, and when we do the substitution, it will cancel out the delta function, but it will leave us a residual term. but we will construct the polynomial in a special way such that the residual term that's left is not a singular term. We will not cause us problems when we solve the partial differential equation. So we tested out with a simple example. Now we tested out with a quadratic transmissivity as a quadratic function. Now it's not a constant anymore. So we used this special trick and we constructed the polynomial in that special way, and we were able to solve the partial differential equation. So we validated that this is a nice little neat trick that we can use to solve the real application problem, the real version of that partial differential equation. Okay, so what was the next level in our research project? Now, so far we have been using constant transmissivity values and a quadratic transmissivity function. So next we moved on to real life data. So now we got data, actual transmissivity values from the geologist. Now remember, geologists use MODFLOW software, and in their software transmissivity values, they are piecewise constant. Now in our problem, when we use radial basis function method, we assume transmissivity to be a smooth function. So what we did is we took this piecewise constant data. See that in this picture you can see small rectangles and different colors in rectangles. That means the t value is different in each rectangle, piecewise constant. Now we took this gigantic piecewise constant data and we interpolated them using the radial basis function method and made them smooth. Remember, we can use radial basis function method in interpolation as well, right? So we converted this piecewise constant data into a smooth function through interpolation. So when we do that, this is how the real life transmissivity values looks like. Now using those real life data, we solve the PDE using the approach that I explained before, and this is how the drawdown. Now this is not upside down, now this is in the correct direction. Okay, this is not flipped. Now this is how the drawdown looks like after 1000 days. Now you can see there are differences in different drawdowns in different areas, and we were able to solve this real life problem using the radial basis function method successfully. And then this is how the contours, drawdown contours looks like when we use the radial basis function method and MODFLOW software. So these black curves, they represent the drawdown contours after 2 days, 30 days and 100 days of pumping, and the red color curves represent the solutions using the MODFLOW software for same amount of days. Now this left hand picture is the contours over the piecewise constant transmissivity, and the second picture is the same contours over the interpolated transmissivity values. Now the biggest advantage with the radial basis function method is that computational efficiency. Now here's what happens. Now these blue color dots, they are the corner points of the rectangles that the MODFLOW use as a mesh. Now these red dots are the number of RBF nodes that's requires to get the same accuracy, same solution comparing to the mesh that's produced by the MODFLOW. So you can see you need smaller number of nodes in RBF method to get the same solution. So it's very efficient comparing to the mesh based method. So the computational efficiency is very high when we use the radial basis function method. So that's my first project that I did as a PhD student to fulfill my thesis work at Michigan Technological University. Now right now we are working on the second project for my thesis work. Now the second project is about the same partial differential equation, but now in the domain, in the geological structure, we have cracks or fractures. Now that's another difficulty. That means, now remember, we have the well represented by a delta function. Now transmissivity in this project, our transmissivity was either a constant or a smooth function. But when you have cracks and fractures, transmissivity is going to be a discontinuous function. So that's going to introduce another singularity in the partial differential equation. So we have two singular terms, the well, and now a singular term from the transmissivity. So we are working on a new method to handle this new singularity as well as the old singularity. So that's what our research group working on right now. Thank you very much for watching this video, and hopefully when we finish the next project, I will do another video series about the new project, and I will upload it in my personal website. So thank you again for watching this video. Bye bye.